Progress in our analytical equipment series videos, we will look into ABG analyzers, which are also known as arterial blood gas analyzers in this video. If you have not seen the rest of analytical equipment videos, you can check out our pathology equipments playlist. Let's start the video from the beginning of blood gas analyzers. Arterial blood gas analyzers have been available for laboratory and point of care, or POC, use for decades. In 1957, John Severinghaus developed the first blood gas analyzer, now located in the Smithsonian, which measured pH, pCO2, and PO2. In the mid-1960s, blood gas analyzers became commercially available and were used primarily in clinical laboratories. As sensors, electronics, and fluidics improved, analyzers became smaller and easier to use, and gradually migrated into POC areas such as respiratory therapy and pulmonary function. With the introduction of new whole blood biosensors, the role of analyzers expanded significantly. In 1985, the first combined blood gas electrolyte analyzer was introduced, with a menu of pH, pCO2, PO2, sodium, calcium, and hematocrit. As additional whole blood biosensors were introduced, blood gas analyzers evolved into comprehensive critical care analyzers capable of performing a broad menu including pH, pCO2, PO2, sodium, chlorine, magnesium, glucose, lactate, urea, creatinine, hematocrit, hemoglobin, O2 saturation, and co-oximetry. Let's learn about the basics of ABG analyzer electrodes. There are many electrodes that have been designed to measure any number of parameters in blood gas analysis. Today we will look into basic electrodes in this video to understand how the chemistry works in different electrodes. First, we will look into reference electrodes. There are two types of half cells, working half cells and reference half cells. The working or measuring half cell is placed at the site where the actual chemical analysis, work, or electrochemical change takes place. The reference half cell is the standard against which the electrochemical change is compared and measured. Reference electrode is nothing but the no value of the measuring value. Second, we will look into the pH electrode. The pH electrode is a glass electrode consisting of a three-dimensional latticework of a central silicon atom surrounded by 4 oxygen atoms. There is incorporation of various metal oxides, calcium cation, and sodium ions into the glass membrane, allowing for variant sensitivity of the electrode. The metal oxides lose electrons to the incorporated oxygen molecules and thus become cations. Charge is displaced across the membrane, resulting in the flow of current across the glass. The one side of the glass is exposed to a buffer of known pH, reference electrode. The other side is exposed to blood, test solution. The glass membrane is then a partition with differing hydrogen ions on either side, establishing a potential difference via the concentration gradient. The pH remains constant despite the change in hydrogen ions due to the action of the inner buffer solution. The third type of electrode is the PaCO2 electrode. The Severinghaus electrode is the mainstay of carbon dioxide measurement from the arterial blood gas. It is essentially a pH electrode, but contains the pH and reference electrodes within one device. The result takes a long time to determine, 1 to 3 minutes, due to the prolonged equilibration and calibration. It is then presented to a thin film of sodium bicarbonate via a silicon or Teflon membrane, which is permeable to CO2 but impermeable to blood cells. This equilibrates with the blood and becomes the test solution. There is a buffer solution held in contact with the silicon membrane by nylon or glass wool. The bicarbonate buffer has a concentration of 0.001 molecules to 1. Prior to use, calibration occurs with 2 gases of known concentration, 4 and 8%, in either a gaseous or liquid state. Reference electrode houses silver chloride, which is direct contact with the buffer solution. Silicon membrane is permeable to CO2, but no other ions that can affect the change of pH. The change in hydrogen ions is read by the voltmeter, which is giving a reading via calibration in units of PaCO2. The fourth type of electrode is PaO2 electrodes. The Clark electrode measures the tension of oxygen in the solution, which is directly proportional or equated to oxygen content of the blood or gas mixture into iron oxide. The principle is that a certain number of O2 molecules within a salt solution will produce a current. Ohm's law is the governing principle. Voltage is equal to current into resistance. The Clark electrode is cheap, reliable, and small, requiring no external power supply. There are 2 electrodes within a single unit, both of which are found behind a single, semi-permeable membrane. There is a polypropylene membrane, which is O2 permeable, preventing bacteria, proteins, and sediment traversing it. These interfere with the measurement and interpretation of the oxygen values, especially the bacteria, which consumes excess O2 and thus skews the values. The determinant of current flow is by use of the polarogram. The next electrode used to measure metabolites like glucose lactate. The measurement of glucose and lactate are vital by a rapid, reliable, and reproducible means. These values are determined by the oxidation of the H2O2 hydrogen peroxide. There are 2 electrodes in the electrolyte solution. It is important to note that there is a silver chloride as cathode and a platinum as an anode, along with this contrast with the Clark electrode. Each electrode is then covered by a 3-layered membrane. Measures current determined by the degree of concentration of glucose or lactate. It is thus calibrated to read glucose or lactate. Let's learn about the working principle of blood gas analyzers. Blood gas and pH analyzers use electrodes to determine pH, partial pressure of carbon dioxide, and partial pressure of oxygen in the blood. Chemistry analyzers use a dry reagent pad system in which a filter pad impregnated with all reagents required for a particular reaction is placed on a thin plastic strip. Electrolyte analyzers use the ion-selective electrode methodology, in which measurements of the ion activity in the solution are made potentiometrically using an external reference electrode and an ISE containing an internal reference electrode. Whole blood samples are placed in tubes, on reaction cuvettes, or on test strips and loaded into the analyzer. The operator may select the tests being performed on the sample using a keypad or connected computer. Operators should be aware of the risk of exposure to potentially infectious bloodborne pathogens during testing procedures and should use universal precautions including wearing gloves, face shields or masks, and gowns. Let's look into the types of blood gas analyzers. There are 2 major types of ABG analyzers available in the market. One is a standalone conventional ABG analyzer and the second is a portable ABG analyzer. First, let's look into the standalone ABG analyzers. In a standalone ABG analyzer, the machine consists of 2 major things. One is the reagents pack, and the second is a sensor cassette, where reagent packs provide necessary reagents to measure the ABG values along with mixing blood samples. The sensor cassettes have all the electrodes which calculate the values of different parameters in blood. The second is a portable or handheld ABG analyzer. This type of ABG analyzer consists of simple cassettes, which consist of different electrodes or sensors, which determine the ABG values directly interacting with the device. This type of device doesn't need any type of reagents or supplies. Only disposable cassettes are used to determine the ABG values for each patient. This type of machine is very helpful for intra-hospital transport in different departments of the hospital. This was a simplified information video on blood gas analyzers, as it's a part of the huge blood gas chemistry. Covering all the points are much more difficult in one video. We will be covering more points on this subject once our channel progresses to the next level, where we can cover more animated concepts which help to understand the theory. Hope you loved this.